Okay, group, this is grade 10 chemistry review. So for the senior chemistry classes, this is going to be really helpful. Now it covers content that we'll need throughout the course. So some of this is a little more important than others. But what I want you to do is just go through this and just try to fill in some of the gaps. You should have at this point completed or attempted all of the questions. So let's just go through these together. I'll try to give some simple definitions with some examples where needed, and you could skip parts if you got the questions. So just go through and pick the parts that are appropriate for you. First question can be a little bit difficult to define terms that we've used before, but elements, generally we're talking about one type of atom. That's really the key thing. And we have to revise this a little bit because even an ion can be in its elemental form. So I'll give some examples. So we could look at, say, a sodium atom. We could look at a chloride ion. We could look at, for example, chlorine gas, which would be a diatomic element, and all of those would be called appropriately elements. Compound, on the other hand, would have two or more types of atoms or ions. So giving some examples here of compounds. A compound has two or more types of atoms or ions. Sodium chloride is made up of ionic units, so sodium and chloride ions. Carbon dioxide gas, we could have calcium phosphate, which is made up of here 5 ions, including a polyatomic group, the phosphate group. It could be a liquid such as ethanol, which has a molecular structure, not ionic, but still made up of 2 or more elements, really. Look at number 2, physical changes and chemical changes. Sometimes the observations can be very hard to distinguish. Let me give some examples. Here's a list. You may have generated a separate list of your own. Generally, I would say the first 3 may be observed for physical change. Bubbles of gas could be when you boil something. Precipitate formed, if you want to think of solidification as a physical change, you could call the formation of ice and water sort of a type of precipitate. You could maybe see light emitted, or you could feel heat emitted or possibly absorbed. Sound emitted is common even with physical changes. Just consider breaking up something into smaller pieces. It's a physical change, but it could make sound like chopping wood. So really the first 3 sometimes can be found in both physical chemical change. Difficult to reverse. Irreversibility as an observation is something that usually indicates chemical change, and definitely a new substance formed with new properties is going to be unique to the chemical change. Okay, for this third question, I just brought up the WHMIS.ca website. WHMIS is Workplace Hazardous Materials Information System. It's a comprehensive training, job site, worker safety system, which is intended to keep people on a workplace safe. Oddly enough, in schools, it doesn't apply to students necessarily because they're not workers. But if you take co-op courses, you'll need to take the training. You might need to get first aid training as well. The symbols themselves are quite recognizable. So the 8 common ones are poisonous material with the skull and crossbones, the toxic material, T with the drop, corrosive material showing damage to metal or skin, compressed gas shows a gas cylinder. You notice all the WHMIS symbols are enclosed in a dark circle. Flammable and combustible materials, the flame, you have your biohazardous infectious material, oxidizing material, and dangerously reactive material. These are symbols you will sometimes see on the chemical bottles that we use in our lab. So just be familiar with the main ones that we're using. In this question, flammability, poisonous, corrosive and explosive are the ones highlighted, but you should be familiar with all those symbols as you encounter them. All right, number 4, law of conservation of mass. Generally, we hold that mass remains the same before and after a chemical change, and specifically in a chemical reaction, mass of the reactants or reactant is equal to the mass of the product or products. All right, when we're going to balance reaction equations, we have to understand what we're doing here is we are ensuring that the reaction equation as written obeys the law of conservation of mass. Now, molecules have mass, and when we write a chemical formula, we're representing a certain number of atoms or ions, or a certain number of molecules, whatever the unit is. It has a mass. So when we indicate the number, the quantity of the unit, we are ensuring that all elements have equal mass on the reactant and product side. So here's some rules you can look at that are good to keep in mind when you're trying to balance chemical equations by the inspection method. If you want to use a model kit, or if you want to make a drawing, that may help as a visual way of representing the chemical formula. But in a balanced chemical equation, we're usually just working with adjusting the coefficients or quantity of units for each of our compounds or elements. So write the chemical formula for each reactant and product. Make sure you get it correct. If you don't, you're probably not going to be able to balance it correctly. Balance everything except for elements typically, and everything except for polyatomic ions first, and then when you're balancing polyatomic ions such as carbonate, nitrate, sulfate, hydroxide, other ones that you'd be familiar with, balance them as a group if they are present on both sides. Then balance any remaining atoms and molecules, and finally balance elements such as hydrogen or oxygen, your diatomics at the end, and then just do a quick check, left side, right side, count the number of atoms or ions of every element and make sure that mass is obeyed. Okay, I'm just going to show the first example here when we're attempting to balance, for example, hydrocarbon combustion reaction. Again, keeping hydrogen and oxygen balanced at the end. We look immediately at carbon as the only other element. We have 6 carbon atoms on the left side. In that molecule, we need to balance that by producing 6 carbon dioxide units, and we cannot change the chemical formula of carbon dioxide, so we never ever tamper with the subscripts. We're just implementing different coefficients. Okay, so now we have 6 O2 units in the carbon dioxide, which is 12 oxygen atoms, so we would need 6 O2 units on the left side. And looking at hydrogen, finally, we have 6 hydrogen atoms on the left side. They come in packets of 2 at a time, so again, we can't adjust the chemical formula for hydrogen, but we can indicate multiple units. So 3 hydrogen molecules would be produced, 6 carbon dioxide molecules, 6 oxygen atoms are required, or oxygen molecules rather, and 1 C6H6 molecule. So again, coefficients there are shown. 1 is implied if it's not indicated. I'm going to just have you pause, try B, C, and D on your own, or if you have already completed them, I'll update them shortly and you can compare your answers. Okay, so B is a synthesis reaction. We have octahedral sulfur. This is the form of sulfur as an element. It exists as an 8-atom group, similar to a molecule, I guess. We could say octahedral sulfur combining with oxygen. All right, that's going to require 8 sulfur dioxide molecules as product. Each molecule has 2 oxygen atoms, which gives us 16 oxygen atoms. So we balance that with 8 O2 groups on the left side. For C, pretty simple. We're only going to need 1 chlorine molecule. However, chlorine is diatomic, so it's going to produce 2 units of sodium chloride, which only contain 1 chloride ion each. So then would require 2 sodium atoms. And what we're really representing here at first glance is the number of atoms and molecules, ions, simple units, but later on in the course these coefficients are going to represent much larger quantities, which we get to when we look at the concept of a mole in chemistry. Alright, and the final one, again, very straightforward, mercury 2 oxide decomposing here to mercury atoms and oxygen molecules, and it's balanced pretty straightforward there again. And number 6, we have the reaction types. There are 5 common reaction types. Sometimes there's a little bit of overlap. Hydrocarbon combustion is unique, although it almost fits a synthesis type reaction, forming more complicated molecules. But in that case, usually the products are pretty predictable: carbon dioxide, water, or in incomplete combustion, we have maybe carbon monoxide, carbon, and water. In A, it's a straightforward synthesis, building up more complicated unit. C is partner exchange, double displacement. A is single displacement, and then E is really opposite to synthesis. It's a decomposition reaction. All right, well, particular elements have group names, and the most common families of elements are the alkali metals, the alkaline earth metals, the noble gases, the halogens, and typically metalloids is a sort of a unique category of its own, which covers several periods and groups or columns. So I've just given some representative elements for group 1, the alkali metals, sodium, rubidium. Group 2, the alkaline earth metals, beryllium and barium. Metalloids are the sort of staircase elements: silicon, arsenic. Noble gases are your group 8 stable elements: argon, for example, or radon, which is Rn, not Rd. And finally, the halogens, which are typically as elements diatomic, so chlorine and iodine as examples. All right, the Bohr-Rutherford model of the atom is not a complete picture of the atom, but 2 key figures in scientific history: Niels Bohr and Ernest Rutherford were both chemists, and Rutherford studied the nucleus, and Bohr looked at electron configurations. So the nucleus is the part of the atom, similar to the nucleus of a cell, which is a small, very small part of the cell, but for an atom, extremely small in volume, very dense, and it is the location of almost all of the mass of an atom. It's a positively charged core. It contains the protons and the neutrons, which are your heavy particles. They're approximately equal in mass, and we give them symbols P and N, and the protons are positively charged, the neutrons have no charge. The other part of the model is that the electrons occupy the rest of the volume of the atom, which is the majority of an atom's volume. They occupy in specific locations. In the Bohr-Rutherford model, they're fixed locations, and these are surrounding the nucleus in orbits or regions, which are usually represented as concentric circles in increasing size, and the electrons load in the first orbit 2 at a time, up to 2, and the second orbit can accommodate up to 8 electrons, the third orbit up to 8, which takes us up to the 18th element, which is argon, and beyond that, potassium and calcium will also be able to fill the 4th orbit, which can accommodate much more than 8 electrons, but for our purposes we can at least include 2 electrons if we're drawing diagrams for potassium or calcium. Alright, so here I've shown some information. A simple little calculation to determine the number of neutrons is the mass number, which is the top number in standard atomic notation. Subtract the atomic number, which is the bottom number. And so the 32 represents 32 heavy particles, 16 of which are protons. The remaining 16 must be neutrons. That information goes into the nucleus of the atom, which has a circle around it in this diagram. The orbits are shown as concentric circles. 2 electrons can occupy the first orbit. The next orbit holds up to 8, so that's 10 of our 16 electrons, and we load electrons in occupying the 4 positions before we start to pair them up. And so sulfur's Bohr-Rutherford diagram would have 2 unpaired electrons in the 3rd orbit, and that 3rd orbit would be called the valence shell or valence orbit. For magnesium, similar, we have 12 protons, which is the same as the number of electrons for every atom, and the number of neutrons, again here for this isotope of magnesium, would also be 12. 24 subtract 12, and our 12 electrons are going to load in as 2, 8, and 2 in their third orbit as well. All right, the main reason why atoms form compounds is because elements on their own are not as stable, and we have to understand that the periodic table of the elements represents the known elements, and yet not are all found in that form. Most aren't, actually. The compound is really evidence of the fact that elements are more stable when bonded together, and that's what a chemical bond is. It's the holding together of a unit of atoms or ions, and that occurs when atoms may lose, gain, or share electrons with other atoms, and that stability is achieved most commonly through a complete or filled valence orbit. And we often think of the third or second or beyond orbits as having the term stable octet associated with them, but a full octet for most of the valence orbits applies, except for the case of helium, which would be a very simple element with only 2 electrons, in which case it's stable, and hydrogen as an atom can achieve a similar electron configuration to helium by gaining or sharing 1 electron with another atom. So stable octet doesn't always apply, but for most of our elements it will. Well, the 2 ways in which atoms combine can really be summed up by the 2 types of bonds, 2 most common types of bonds which are possible, which are ionic and covalent. Both involve electrons. When we think of a chemical bond, electrons are always involved. And in the ionic case, electrons are transferred between 2 or more metal and nonmetal atoms. And in the case of the covalent, we think of co as a sharing or a cooperation. Valent refers to the valence orbit. The electrons in that are shared between 2 or more nonmetal atoms. All right, so I've filled in C here for you. I've got some ionic compounds, which in this case, they all contain monovalent metal ions, meaning that there is only 1 possible charge for each of them. And we'll look at the polyvalent or multivalent metal ions and their naming a little bit later, and their chemical formulas are just slightly different in how we generate them. But for ionic compounds and molecular compounds or covalent, the ending is almost universally IDE, unless we're talking about polyatomic groups, but IDE is common. You'll notice that in all of the cases. The metal name is never modified. The nonmetal name, if appropriate for ionic compounds, is the prefix of the name followed by the truncated portion at the end, replaced with IDE. So oxygen gets cut off and replaced with oxide. Now, when we're generating the chemical formula from a name, best to just start with the charges of our ions, and that's coming from the periodic table, looking at the number of valence electrons that are lost or gained, and that is a simple matter of looking at the chemical column or group where the element is found and moving towards the nearest noble gas. Sodium is much nearer to neon than it is to argon, so we'll lose 1 valence electron. Oxygen, as a group 6 element, is nearer to neon than it is to helium, and it will gain 2 electrons, and the charges are determined by number of electrons gained would be the negative charge, number of electrons lost would be the positive charge. So ions need to be balanced in the formation of an ionic compound, so we'll need 2 positive 1 ions and 1 negative 2 oxide ions, so our formula would be Na2O. Lithium and iodide have a balance of charges already. Their valences are +1 and -1 respectively, so Li. And for the last 4, these are covalent, so you'll notice the prefixes will be important in covalent compound naming, but never in ionic compounds. The naming is very easy for ionic compounds. Carbon dioxide indicates 2 oxygen atoms, 1 carbon atom, silicon tetrabromide, 4 bromine atoms in that molecule, sulfur dioxide, and nitrogen tribromide. Again, notice the IDE ending and just the use of a simple prefix before the root name of the nonmetal. All right, well, first what I decided to do is make sure you're familiar with some of the main points in the kinetic molecular theory. So kinetic refers to motion of molecules in this theory, and fairly common sense. Molecules, although they're not visible, we see the evidence of molecules. If you smell perfume after a bottle of perfume has been opened, you know that your nose is inhaling molecules which have moved from one location in the room to your location. So molecules must be in constant random motion. Molecules we do observe move faster when the temperature increases. We certainly can relate to that when we see how, for example, a drop of food coloring disperses in a glass of water, and as the temperature of the water increases, the distribution of the dye is made faster. Molecules, on the other hand, would move slower when the temperature drops. And in terms of a reaction, molecules must collide or come into contact for a reaction to occur. All right, I'll just list the 4 most common factors that affect a reaction's rate, and that will be something we study more in the grade 12 course. But reaction rate, you certainly observe it when you carry out experiments, and how quickly the reaction comes to completion. In order here, not necessarily of importance, would be surface area. That's the form of the compound or element. It could be a solid chunk, could be grains, could be fine powder, could be a dissolved solute in solution form. And as we progress, the surface area increases, meaning the particles are smaller and they're spread out over a greater area, and they're more likely to come into contact with other reactants and collide. Temperature has been mentioned already. The warmer the reaction solution or the reaction temperature, the faster molecules will move. They'll hit each other with more energy, and they'll be more likely to have a successful reaction. Concentration refers to really how much reactant is present. Higher concentration, obviously, we're going to have more particles, so it's greater chance for them to come in contact with other reactants. And the last one is other reaction conditions. So, for example, if it's gas phase reaction, it could be pressure. If it's a reaction where a catalyst is needed, the presence of a catalyst in some cases will prevent a reaction from occurring. Students who've looked at biology and studied maybe senior biology would be familiar with enzymes as an example of a catalyst, something which is not consumed but helps the molecules come into contact with each other. Okay, now depending on how much pH scale, acid-base content you studied in previous grades, hopefully you're familiar with the different range of common pH values. This is the common scale from 0 to 14. It does actually extend beyond 0 into the negatives and beyond 14 into higher values. But the common range of most chemicals is 0 to 14, with 7 being neutral, below 7 being the acidic range, and above 7 being the basic range. The representative ion for the acidic nature of a compound is the H plus or hydrogen ion, and the OH negative or hydroxide ion. Okay, and a neutralization reaction would be taking either an acid or a base and bringing the pH into a range closer to 7. And so both acids and bases have, so here our products are salt and water in any neutralization reaction. So I just use common acid, hydrochloric acid, hydrogen chloride, and very common base, sodium hydroxide, would give the salt NaCl and water H2O. A salt, generally when we refer to just I mentioned is not always table salt. It could be any ionic solid. It can be referred to as a salt. All right, it's known that the two of the most common chemical pollutants that are leading causes of acid precipitation are sulfur dioxide and nitrogen oxides. NOx would be the sort of general formula for any compound containing nitrogen and one or more oxygen atoms. They're both gases, and they're both found in fuels, diesel, gasoline, and other hydrocarbons. When they're burned, they quite often contain sulfur levels and nitrogen levels, which are going to be released as pollutant gases. All right, now it's quite likely that many of you didn't encounter this series of reaction equations, word equations. However, it's not too difficult to look this up in a previous textbook, and that's what I've done. The content here is reactants going to products. We're looking at chemical formulae. We're balancing them. So this is within our abilities at this point. Starting in the grade 11 course, you'll be needing to do a little bit more independent research. So looking up the chain of reactions to produce acid rain as one component would be nitric acid. Involves three main reactants, as atmospheric chemists have told us. First one would be the oxidation or combustion, and we could call it, of nitrogen, combining with O2 gas, and we're producing nitrogen monoxide as an intermediate. That further combusts or burns in the presence of oxygen to produce nitrogen dioxide, also a gas, which combines with water vapor, which is abundant in the atmosphere, to produce nitric acid or hydrogen nitrate, which would be dissolved in those water droplets as aqueous acid and more nitrogen monoxide. And it's this nitric acid here which is going to fall as acid deposition. It could be commonly rain, or it could fall as acid mist, or it could even be in the form of snow or ice pellets. Anything containing water will probably have this acid dissolved. Okay, and the second set of reactions involves the conversion of elemental sulfur to sulfuric acid, or aqueous hydrogen sulfate, as we would correctly name it, as an acid. So we're starting with octahedral sulfur, and we've seen a similar reaction balance before with oxygen. That produces sulfur dioxide, which in turn combines with oxygen again to form the final sulfur oxide, the trioxide gas, which when it combines with atmospheric water will produce the H2SO4 molecule, which again is dissolved in the water droplets, and that also is going to fall as acid deposition. All right, at this point, I'm leaving this with you to approach me if you're having serious difficulties with some concepts. I would encourage you to sign out a grade 10 textbook and keep it for a week or two, longer if you need, just to help you establish some of these fundamentals, and just move forward from here with understanding that there may be some gaps that you'll have to work out, and there'll be additional instruction on quite a lot of this content, so you'll see it again before it's expected that you know this for other learning. Thank you.